That's too big. All right, we have our problem, and we've now taken all the information and entered it into ease. And what we're trying to do here is we'll come up with the boundary conditions. We have a system of equations. We have our general solution. We want to plug it all in and maybe solve for like the temperature at r equals 0. Like, are we okay? Is our hay bale going to start on fire and ruin the farm? Right. So we want to figure out what the temperature is at r equals 0, which is going to be the highest temperature. Right? That's the farthest that heat has to go. So let's go through and entered all the information that's given. Again, enter the value, the units, and then convert them appropriately. And then we're calculating here the plastic conduction. That's what we just entered. Could do it this way too. The plastic conduction resistance, the convection resistance. I guess here I've decided thickness is actually small enough that it's essentially the radius of the bale. Doesn't exactly match. And then I've got an equation here which is saying this is basically enforcing our boundary conditions. This is the part that I skipped at the end. But you're taking the temperature, substituting that in here. So you have T at the outer radius minus T infinity over the total resistance. And then here on the left-hand side we have the heat flow. Okay, so this is the second boundary condition. What you'll notice is I didn't bother solving for C2. Right? We said C1 was 0. I didn't even bother solving for C2 because I know ease can calculate that for me. I just enter the equation. All this other stuff is known. I just enter the equation that includes C2. Evaluated this whole thing at r equals r bale, I guess is what I called it here. And we're left being able to compute C2. I'm evaluating this at r equals 0, and then I have my general solution here. So this generation term, C1 went away. And we're left with just C2, which I can compute using this equation. All right. So that's as far as I needed to go there. And we can actually run this. All right. So if I run this, I find, now evaluating at r equals 0, that my temperature at r equals 0 is 120.6 Fahrenheit. So I'm below 170, and that's fine, right? No problem. One thing you might want to do is plot this. So we could, for those who have not used these in a while, you can create a new parametric table. So we'd go new parametric table here, which would create a table. You set the number of rows that you want, and then you pick the things that you want to, so like if we went to this dialog, you could pick the things that you want to include in the table. And let's say we want to look at the temperature as a function of the radius. So we could do that. Enter the values for radius. You click this little drop down, your first value and your last value. So this happens to be r bale. It'll enter it in. And then you click this little green arrow or hit F3, and it'll run it. Now before you do that, you have to go back into your equations window, and you have to comment out the thing that you're varying. So if we're setting in the parametric table the radius, you have to make sure to comment it out. Otherwise, it's going to say you've got too many equations and not enough unknowns. Okay, so I've already done this. We look at the table, and we're seeing now the temperature in degrees Fahrenheit as a function of radial position, which goes all the way down. And then we could create a plot. So up here, we'd say new plot window. I've again already done this. And we plot out our temperature as a function of position. Right, so take a moment to look at this. We have at the radius, the outer radius, we have the basically ambient temperature that we said it was going to go to. We have the hottest temperature at the inner point. Right, that makes sense. But this is maybe a good way of understanding the result that you're getting out of this. Okay. Any questions on the ease part? Again, this example is in the folder if you want it. Okay. So one thing that we could do, So ease is not all I have here. I have, you can do the exact same thing in Python. So I put up that video that said, hey, use VS Code. Turns out Spider is installed on the CIE computer, so I'll just use that to show you. But I would, again, recommend that you use VS Code if you're doing it yourself. OK, so in Python, you can do exactly the same thing, but there's some things to maybe point out. First thing is, if you happen to download this code like last night, there was an error. I divided by or multiplied by this instead of dividing anyway. So you want to get the code from today. But a couple things to note: you have to handle all the unit conversions yourself, right? So that's maybe slightly annoying, but there's really no good way around that. But you enter in all the data. You do the same calculations. Most of this is just copy paste from ease. The tricky part, though, is we said ease can take the job of calculating C2, right? So C2 appears in this equation on the right-hand side. Programming languages like Python and others can't deal with that, right? There's no way to do this implicit solution. So rather than, I mean, you could go back and solve it analytically, but another easy way of dealing with that is to use this scipy.optimize library. There's a function called root scalar. So if you can get everything to kind of come down to one equation where the equation is implicit, you can use this root scalar method to program in your function. Maybe it's hard to see. We have the function. There's the left-hand side equals the right-hand side. This is straight from our boundary condition. What we actually want to do is figure out a value for C2 that makes this expression true, right? And another way of saying that is if I took the left-hand side minus the right-hand side, it has to equal 0. So we're trying to find a value for C2 when the left-hand side minus the right-hand side equals 0, which is exactly what this root scalar function will do for you. It'll find the value of C2. I'm going to give it C2 as my independent variable. And it's going to find the value that minimizes this or finds the root at 0. So you can just follow this template. There's other functions if you have more complex systems of equations. We'll get into that later. But if you just have like one equation and you want to do it this way, this is how you do it. So here we're calculating C2. We're getting the value of the root, assigning that to C2, and then we can use that in our general solution. Okay. So we do the same thing. So you could run this, I think. Runs instantaneously because it's a really simple program. And we see that our temperature is 322.3 at the point we're evaluating at. Here, r equals 0. Everything else should kind of line up. If I look back at the ease solution, I should see 322.3. Right, so these things all agree. There's just multiple ways of doing the same thing. So when you're say doing your homework, I might tell you, you probably want to use ease or probably want to use Python for this particular problem, but you're always free to try it either way. Ease is probably the mostly fail-safe way for analytical solutions. When we get to numerical solutions, we'll have to start using Python. Okay, yeah.
For the unit conversions, you can do them like ease in Python. There's a module called Pint.
Yeah, so that's a good point. There are lots of tools in Python that can help you with units. One thing that I've found, and maybe I just am too dumb to figure it out, but I found that if you include everything with units, when you start integrating like SciPy to optimize stuff and NumPy stuff, those don't like the unit things accompanying them. So then you have to like scrub out the units to use those. So I don't recommend you try that unless you know what you're doing, but you can do it. Okay. Any questions on this? We have about 3-4 minutes left. Okay. So last thing I want to talk about is, let's go back here. Last thing I want to talk about is this idea that I think in one of the first lectures I said, if you have thermal generation, you can't use resistance, or you shouldn't use it. Let me add a little nuance to that, right? So you can use a resistance network for problems with thermal generation. You just have to understand that it's a little bit wrong, right? It's a little bit, the answer is a little bit incorrect. And depending on how you use it, you can be very incorrect or a little incorrect. If you use it very carefully and you know what you're doing, you can pretty much get the same answer out of a resistance model as you can out of an analytical solution that includes thermal generation. So let's go through this example really quickly with thermal generation, and I'll just kind of give you the values as we're going through here. So let's we have our hay bale here. We have position R, but if we model this, you can say that there's a thermal resistance due to conduction, and then there's this like plastic layer, right? So there's a thermal resistance due to the plastic layer. Then there's a thermal resistance due to convection. So we might call this R conduction of the bale, R conduction of the plastic, R convection. And we know this temperature out here to be T infinity. And one way you could model this is, let's say, I know I'm generating heat. There's some G dot. There's a total G dot associated with this hay bale. I could say I want all that G dot to go through this conduction resistance. So that's basically saying I have all of my generation happening at R equals 0. It has to find a way to conduct out. Or maybe all that generation is happening at some position R, and it all has to find a way to conduct out. But if I do that computation, that's going to set an upper bound on that temperature, right? And if I do that and find that that temperature is fine, then I don't have to go further. I don't have to do the analytical solution, right? So we go through. So let me just give you the values. If you go through and the one maybe nuance is let's say R conduction of the bale. So what's my, again, using a really approximate model, what's my, say, average length that heat has to travel when it's being conducted through this bale? Could be the radius, but say the average, like, you know, not all the generation is going to happen at R equals 0. So pick some other value, right? Maybe on average, heat has to travel half the way or something. If you did an integral, you might find that it's more like it only has to travel a third of the way because there's more volume as you go to larger radii. But let's say, okay, R conduction bale, the average length that you have to travel is, where am I here? R bale over 2. All right, so that's our thickness for conduction. And then we have K times the area for conduction, which would be 2 pi, let's say R bale L. All right. Now, you look at this and you might think factors of 2, like, does it quite line up? What about the area? What do you mean, like, area for conduction? If you're doing that, you're kind of missing the point, right? The point here is we're going to use an approximate model. So we can argue about factors of 2. We can argue about the areas. But this is just supposed to get you close. All right? So if we do that, we keep all the other resistances the same. We end up finding that this resistance is 1.99 Kelvin per watt. This resistance here is, what, 0.0008 Kelvin per watt. This resistance is 0.01 Kelvin per watt. And you could model it in ease very easily. But what you see is, like, we went through that trouble. We could have basically said T infinity is equal to the edge of the bale, right, and been fine. So we kind of wasted our time a little. But I'll just show you the result when you calculate this in ease. So we go back here. I've introduced this model, R conduction bale here. All that G dot is going through, and then we're approximating the T max. And the kind of funny thing is that our T max approximate is what, exactly equal to RT. Okay? So we did a lot of work for nothing. But we actually kind of got lucky because we picked R bale over 2, and you could have picked any other value. But it's just proving the point that there's still a lot of value to be had in using resistance network models for problems with generation. You just have to know the right way to use it.